All right, in this video here, we are going to graph the function y equals sine of theta minus 2 pi. Now, what's different about this one is we're actually creating a transformation by affecting the theta prior to evaluating the sine function. So this is actually going to make a different kind of transformation than we've seen before. So I've got this parent function sketched already. I've got my table of values set up from the parent function, and we're just going to start to plug some things in for theta. So the first thing I want to do is I want to start off by plugging in negative 2 pi for theta. So let's do this down in the bottom here. And so we're going to take negative 2 pi and plug that right in for theta and solve for y. So y is going to equal sine of negative 2 pi minus pi over 2. And that's the same thing as the sine of negative 4 pi over 2 minus pi over 2. So that's negative 5 pi over 2. And if I think about what that's equal to, I can just kind of break this down by thinking about the unit circle. And I can think about starting at 0 radians. And since I have a negative angle, I'm going to go in the clockwise position all the way around until I hit 5 pi, or negative 5 pi over 2. It looks like the y value there is negative 1. So I'm going to set that equal then to negative 1. The y value is negative 1 when theta equals negative 2 pi. Up next, I'm going to evaluate when theta is equal to negative 3 pi over 2. So let's get rid of this right here. And let's plug in negative 3 pi over 2 for theta. So y is going to equal sine of negative 3 pi over 2 minus pi over 2. And if I simplify that, that's going to be the sine of negative 4 pi over 2, also known as negative 2 pi. All right, and negative 2 pi, if I go back to my unit circle and I start 0 radians and go clockwise, that'll be negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. So it looks like the y value there is 1. So that gives me another value on my graph. Or excuse me, equals 0, not 1. Okay, so we'll get rid of that. And let's just plug in negative pi next. So that's the next value in my table. So if I take negative pi minus pi over 2, that's equal to negative 3 pi over 2. And I go back to my unit circle. And if I trace out where negative 3 pi over 2 is, starting at 0 radians, going clockwise, that's negative pi over 2, negative 3 pi over 2. And then that's going to equal positive 1, since that's where my y value is at negative 3 pi over 2. All right, so that's going to be 1 there. And then from there, you can kind of start to see where I'm continuing this pattern, where every single value is just another quarter turn counterclockwise in the positive direction. So I can just continue to use that pattern of 0, and then that'll be negative 1, and then back up to 0, then up to 1, and down to 0, and then down to negative 1. And if you don't believe me, go ahead and actually plug in those values and just confirm for yourself that all of those y values are in fact accurate. So once I have that, I can start to put some of these points down on my curve. And I can graph the new function y equals sine of theta minus pi over 2. So let's start plotting negative 2 pi radians as associated with the y value of negative 1. Negative 3 pi over 2 is 0. Negative pi is 1. Negative pi over 2 is 0. 0 is negative 1. Pi over 2 radians is 0. And then up to 1. And then back down to 0. And then back down to negative 1. So it's a very similar pattern. It does the exact same thing. It goes up and down in this kind of periodic wave-like manner, just like my other sine curves. And actually this over here, I shouldn't keep going down. It's going to actually bend and come back up, since that's my minimum right there. Okay, so I have this graph, and looks very similar. It has really all the same points, just everything has kind of been shifted. So imagine I have these two waves on top of themselves, and then I just kind of drag one across the way. That's what's causing this shifting going on. It's a horizontal transformation where I haven't moved this up or down or left or right, but I'm actually starting my graph, if you were to think of a starting point for my wave, actually at a different position. So we have actually a term for this, and that's called a phase shift. I've taken one phase or one wave of my function, and I've shifted it over. And in this case, I shifted it over to the right. And you can tell that I'm doing that because you can think of the starting point, starting from 0, is now moved over to pi over 2. And the reason that happens is because of this this negative pi over 2 inside with my theta. So you can see I kind of shifted to the right, pi over 2, and because I'm subtracting pi over 2 inside of my sine function, that causes a right phase shift by a number of pi over 2. So that's really where this comes down to, and we'll kind of see more of these examples of how we shift things left or right, but we call it phase shift because the function really goes on forever in both directions. So it doesn't really have like a starting point, but you can think of it as like a certain wave normally starts at 0, but we've shifted it to the right, pi over 2. So, okay, well, let's talk about all of our properties then. The domain, that's still the same. That's negative infinity to infinity. The range, that hasn't changed at all. That's still from -1 to a +1. And then the period is still the same thing. I can trace from one crest or one peak to one peak, and that distance is still exactly the same. Or I could take even from the bottom of the wave to where it reaches the bottom again. It's still 2 pi. Just because I've shifted the wave doesn't change that. And then the amplitude again is still the midline from to the height or to the maximum, and that's still a size of 1. So we've just moved this thing left or right, and it's kind of hard to tell just from the properties that this has happened. So we kind of need to see the graph to see this phase shift.